Okay, everybody, we are back at it in Chapter 17. We finished up our discussion of the buffers in Chapter 16 and titrations, and Chapter 17 deals with more equilibria, but now it's solubility equilibria. So if you think back to those problems that we had last semester with solubility rules, and is this salt soluble or is that salt soluble, and all silver salts are insoluble except for a few, and those kinds of things. Those rules that we talked about last semester are going to come back to us again now as equilibria problems, because every salt that was listed as insoluble in that table is actually sparingly soluble. We call them insoluble because they appear to not dissolve at all in solution, because we put in a tiny amount and it remains, it doesn't dissolve. But tiny fractions of those molecules do ionize and dissolve and dissociate into solution, but we can only make very, very small concentrations before we reach the solubility limit. And for those insoluble compounds, the solubility limit is so low that we just call them insoluble. So in terms of solubility equilibria, we're dealing with sparingly soluble salts. So we can only make dilute solutions. So these solutions are easy to saturate with that solute. So for example, one of the classic first compounds that you deal with in terms of solubility equilibria is solid silver chloride, AgCl. And solid silver chloride is not soluble in water. It was not one of those compounds that was listed as soluble in your solubility rules. So when we take a small amount of it and put it in water, we do get some Ag plus aqueous and Cl minus aqueous, but not very much compared to how many molecules or formula units of silver chloride we put in there. So since this is an equilibrium, this must also have a Kc value associated with it. And the Kc value is going to be still products over reactants. But notice that our only reactant is a solid, and solids don't show up in K expressions. We ignore them. So Kc, which we would normally write as Ag plus, Cl minus, over AgCl, well, we don't write that because it's a solid. And because of that, we don't say it's Kc anymore when we're dealing with these sparingly soluble salts. We call it KSP for the solubility product. So in all of these compounds that we're going to write all these KSP expressions for, it's all about the product ions that are generated. So the count of them in the terms of the coefficient comes from the subscripts. And here it was 1 to 1, so it was 1 and 1. If these are not 1 to 1 subscripts, there won't be 1 to 1 coefficients on the other side. So for this compound, KSP is equal to just Ag plus times Cl minus, again, each to the first power because the coefficients are 1 up here in the overall equation. So working problems like this, we can calculate from KSP the concentration of AgCl that's present in the solution. It'll be very small because it's an insoluble compound. We can also calculate the concentration of Ag plus and Cl minus from all of that using stoichiometry. So as we work our examples, we're going to see situations where we calculate the molar concentration of the compound, or what is the molar concentration of the metal ion, or what is the molar concentration of the anion for those substances in a saturated solution. That means we have reached equilibrium. We put some silver chloride solid into a container, we let it sit until no more is going to dissolve, and then we can do our calculating. So when we come back, we're going to look at some examples of how to write these KSP expressions directly from the substances without necessarily writing out the equations to go along with it. Okay, stay tuned, guys.